Okay. So should I start now?
Okay, so we are very happy to have Yuan for today's Bootstrap seminar, and Yuan is going to tell us about his work on bootstrapping QED3 with 4 colors. Please.
Thank you very much. It is a great honor to me to be invited here to give a talk in the Bootstrap seminars. So today I will discuss bootstrapping conformal 4-flavor QED in 3 dimension based on the work that we published a few months ago in collaboration with the Yale group. The other group members are Soner Albirak, now a postdoc at Amsterdam, student Rajiv Aramili, postdoc Jijin Li, Professor David Poland, and myself. Quantum electrodynamic in 3 dimension is one of the simplest strongly coupled gauge theory. People are interested in this theory because it shares a lot of qualitative similarity with the 4-dimensional QCD. For example, when QED3 is coupled with 0 flavors, it can be proven that the theory has confinement and chiral symmetry breaking due to the monopole proliferation. On the other hand, if we go to large flavor number, here NF, well, so the theory has SU and NF global symmetry. So if NF is large, then we have a large N expansion and the theory is perturbative. And it can be shown that the IR fixed point in this limit is interacting CFT. And it's a crucial unanswered question: what is the lower edge of the conformal window? A lot of work has tried to give an estimation, and the estimation goes all the way from NF is equal to 0 to NF is equal to 10. The reason why it's hard is because for small NF, the theory is non-perturbative. In principle, since the lattice simulation is non-perturbative, it should give us kind of a more reliable result. But there are different works in the lattice simulation give different results in this question. For example, some of the results says there's no chiral symmetry breaking for any positive number NF, but there are some other works saying that NF is equal to 2 has chiral symmetry breaking and is gapped. So this kind of ambiguity is at least partially related to the walking behavior. That is, if one believes in the merger and annihilation scenario, then, for example, NF is equal to 2 could be, the conformal symmetry here could be broken by a small non-unitary factor. If that's true, then it's going to be difficult for methods like the lattice simulation to detect the small gap in the finite volume study. So that's a bit of the history showing that there's a lot of good motivation to study the conformal QED3. And in our work, we consider the 4-flavor QED3, which is generally believed to be conformal. But since it's non-perturbative and it's near the edge of near the lower bound of the conformal window, so it's kind of still non-perturbative. So all of the determination of the conformal indices are far from clear. And besides,
sorry to interrupt, is there a consensus or at least an estimate in the lattice community about the NF, the critical value of NF, or it's all over the place?
Let me think. I'm not sure. I think there are works saying like, okay, so definitely for the work that says for all, there's no chiral symmetry breaking. They kind of imply that like NF is equal to 4 is conformal. And for the work that says NF is equal to 2, it has chiral symmetry breaking, they say they don't know about the status of NF is equal to 4 because the numerics there is a bit hard. Yeah, that's what I know. So I think
so NF equal to 2 could also be conformal. That's been ruled out. I didn't get it.
I think it's some lattice work says NF is equal to 2 is conformal and some says not.
Okay.
And there are like, I think most of the work that says something about NF is equal to 4, it's says it's conformal. Yeah, for the lattice. And besides this, 4-flavor QED3 also has the possible relationship with the Dirac spin liquid in the condensed matter theory. So in principle, there could be many interesting applications in the context of condensed matter. So that also is a good motivation of studying this, this model. On the other hand, over the past decade, conformal bootstrap has been proven to be very successful in solving strongly coupled matters. There are many successful stories. For example, it has set a world record precise solution in providing a precise solution to the 3D Ising model. It has addressed the inconsistency between the experiment and the Monte Carlo simulation in the O2 model. And it also has proven the Heisenberg magnets, which is the O3, 3D O3 model, have a cubic instability, which is kind of a long puzzle. With all of these successful stories, one could ask, can we repeat some of these success in the context of bootstrapping gauge theory? So in this talk, I will try to present that, okay, so there are some challenges that we face in bootstrapping gauge fields, and there are some approaches that we could try to at least partially resolve those issues. A little bit of bootstrap setup. Conformal bootstrap uses crossing symmetry, which says 4-point functions has 2 equivalent operator product expansions, which results in a sum rule in an arbitrary dimensional vector space with positive coefficients. With this crossing equation, the way that we extract bounds is proved by contradiction. If we show that all vectors under certain assumptions sit on one side of a hyperplane, then the sum rule cannot be satisfied with positive coefficients. So one can use that to allow/disallow certain assumptions, and in that way, eventually carve out the parameter space of the target theory. And numerically, we use SDPB or some other or some other convex optimization programs to efficiently find the plane alpha. So that's the basic setup for conformal bootstrap. Since the audience are mostly experts of bootstrap, I'll not spend much time in discussing the technical details in the setup. So let's discuss what we know about QED3. So QED3 is NF flavors of fundamental 2-component fermions coupled with a abelian gauge field. There's a special property to the QED3, that is, it has a topological U1 conserved current. And under this topological U1 global symmetry, there are operators, the so-called monopole operators that are charged under this symmetry, and the monopole charge are quantized to be half integers. These monopole sectors are important because it gives us a handle to distinguish between the U1 abelian gauge field and SUN non-abelian gauge field. The bootstrap target are the low-lying operators, scaling dimensions, and the conserved current central charges. Like I said in the last slide, the operator content includes the monopole operators of different U1 charge and gauge invariant combinations of fermions. And for example, we have the fermion bilinears, 4 fermion operators, and more complicated stuff. And in our work, we take the external operators of the correlator system to be the charge 1/2 monopole, the lowest, the leading monopole, and the fermion adjoint bilinear operator. All of the operators in our system are charged under the flavor SU4 global symmetry, the topological U1 group, and space-time parity. Here is the OPE selection rule in different sectors of our 4-point functions. And let me explain the notation a little bit. The letter SATV represent the topological U1 symmetry in terms of the isomorphic SO2 representations. So the S stands for the singlet representation of SO2, which is also the U1 neutral parity even representation. The SO2 anti-symmetry representation, anti-symmetric tensor representation A is isomorphic to the singlet, but importantly, it has odd parity. And the T stands for the symmetric traceless representation of SO2, which in the U1 language has a monopole charge Q is equal to 1, and this channel can have both parities. And V is the vector representation of SO2. In the U1 language, is Q is equal to 1/2 monopoles, and also can have both parities. The 3-digit index represents the SU4 representation of the operator. It's 3 digits because it represents the number of boxes in the Yuan diagram. Since we study SU4, the Yuan diagram can have at most 3 rows. For example, the singlet representation has no SU4 index, so it's in the at 0, 0, 0 representation. The adjoint representation has one fundamental index and one anti-fundamental index, which trades which we can trade with 3 fundamental index. So it's in the 2, 1, 1 representation, and yeah, etc. So there are a bunch of representations, and we kind of all give a name for it. So I'll try to be clear when we encounter some of these representations in when we talk about the gap assumptions and the bootstrap bounds. And last, the monopole themselves are charged under the SU4 global symmetry with some non-trivial representations. The representation, depending on the monopole charge, have 2 rows and 2 Q columns. So in the OPE, for example, the charge 1/2 monopole will be in the 1, 1, 0 representation, which is this representation, and it shows up in the V 1, 1, 0 representation and shows up in the RM OPE. And the charge 1 monopole is in the 2, 2, 0 representation, and it lives in the T220 representation that appears in the MMOP. M here is the charge 1/2 monopole. So that's the basic structure of QED3 and the OPE selection rule. Oh, by the way, the plus and minus here is the spin selection rule. So depending on the representation, spin, some specific spin, even or odd, are allowed / disallowed in the representation. So there are a bunch of selection rules, and we could ask, what else do we know about QED3 for 4 flavors? In our work, we have found 1/NF expansion results from various sources. If we plug in the number NF is equal to 4, we will get a prediction of the scaling dimensions of the low-lying operators and the conserved current central charges. For example, the external operators we consider are the M1/2 and R, and we found that the large N prediction are 1.02 and 1.43. And we also found a bunch of other scaling dimension large N predictions, which I will show in the next slide. We also found lattice results. The scaling dimension of the R, the adjoint fermion bilinear, is 1.4 from the lattice simulation, and it's basically consistent with the large N prediction. And we also found the lattice simulation of delta M1/2, and that prediction is 1.26, so it's a little bit further away from the large N prediction. So here, as promised, there are a bunch of other operators, large N prediction. Some of them are calculated to the 1/NF or order 1 in the large N prediction. Some of them we only have the leading kind of a leading order in large NF prediction. So we found them from various sources, and very interestingly from the work by Chester, DSU, and Mazai and Pufu in 2017. There is a kind of an oscillator construction of like our large N prediction of these operators, including like fermionic operators and monopole operators. And yeah, we plug in the numbers and we got some predictions. So I'll come back to this table when we talk about specific predictions from these numbers. Now I would like to discuss a little bit of why it's difficult to bootstrap gauge theories. So I'll start with a point that is the most obvious, which is gauge group itself does not show up as a direct input in the crossing equations. So as a consequence of that, the crossing equations for the U1, say U1 fermion bilinear bootstrap and the SUNC fermion bilinear bootstrap are identical. So without further assumptions, one cannot distinguish the bootstrap bounds from of these two theories, which is like one difficulty. And moreover,
sorry, I just want to interject. I mean, it does affect the crossing equations because it affects the representations of monopole operators. So depending on the gauge group, they have
exactly. I'm going to mention it. Yeah. So
okay.
So it affects some of the crossing equation. The fact that there are special topological sectors resolve this this problem. Yeah. But one could be worried if we only talk about say the fermion bilinear bootstrap, right? And yeah, so yeah, another difficulty, okay, so the fundamental fields don't show up as gauge invariant operators in the 4-point functions. So we'll have to use composite operators, which generally have larger scaling dimensions and larger, yeah, so their anomalous dimension is less under control. So those will bring some numerical difficulty together with some ambiguities when we make assumptions. So the possible solution, like Shai just mentioned, okay, so for in the context of Yuan gauge theory, we have the monopole sector, and that resolved this issue. And there are, so one could ask this question, like, what if the gauge group is UK? I guess in that case, one can also construct a topological U1 conserved current out of the trace of the gauge group. In that case, there's also monopoles. And the way that we resolve that degeneracy is by looking at the conserved current central charges, which kind of played an important role later in our study. So the central charges measure the degrees of freedom roughly. So we should expect that these numbers are gonna depend on the number of colors, and indeed the large M prediction of the central charge of the stress tensor and the central charge of the flavor current is proportional to NC. So that tells us the bootstrap bound for the conserved current central charges are going to depend a lot on the number of color. So that gives us a way to distinguish U1 versus, say, UNC type of gauge theories. So so we have tools to distinguish different gauge groups. Another point that is
Sorry, can I ask a question? If you had Chern-Simons coupling, how would it enter into these formulas? Would it be proportional or would it be some kind of subleading thing?
I think it'll be subleading, right?
Is that obvious? I mean, because there's some cases where I think at least supersymmetric cases where I would think CT would be proportional to K and some power of K.
From these two equations, I don't think it. Okay. So the honest answer is I don't really know. So yeah, just by looking at these large M predictions, well, these large M predictions did not. I'm not sure. I don't think it assumes that there's Chern-Simons coupling. So I'm not sure what's gonna happen when the Chern-Simons coupling enters. But I think if we just count the field in the UV, then it looks like it doesn't change the number. At least it doesn't change the number of free fields. But this is very naive. I don't really know. Yeah, but maybe it changes the representations of certain fields, and that changes the large N prediction. So yeah, okay. Another point that is kind of non-obvious is that SUN symmetric correlator bootstrap bound will have a coincidental constraint with that of an SON correlator. For example, in the fermion bilinear bootstrap, fermion bilinear single correlator bootstrap, one can write down linear relation that kind of maps the SU4 representations to the SU4 crossing equations to the SO15 vector single correlator bootstrap crossing equations. And if we look at the monopole single correlator bootstrap, there's also a relationship that relays the representation in the monopole OPE to the SO12 vector single correlator bootstrap. So without further gap assumptions that break those enhanced symmetries, one will get very generic bound that basically associated with this enhanced symmetry. So if your goal is to get the bound on a specific theory that is gap independent, then this sounds very bad because you basically have to solely rely on the gap assumptions to get a specific bootstrap bound. Well, get bootstrap bound for the specific theory. So with this issue, we are kind of we'll have to take a less ambitious goal. That is to say, can we verify or check if the prediction from the large N can form a consistent bootstrap solution? If yes, then using the gap assumptions inspired by those large N predictions, can we use bootstrap to narrow down the parameter space of this special solution? So that will be our goal in this work. So let me show a little bit more details of how we're going to use the large N predictions to kind of bring in some symmetry breaking factors in those crossing equations. So first, if you look at the RRRR single correlator bootstrap, we see that there are a bunch of representations, the adjoint, the A bar representation, and this 422 is what we call the SS bar. And these three channels are mapped to the same representation in the SO15 vector bootstrap. And if we look at the large N prediction, then the leading contribution is all 4 fermion operators, and there are subleading 1/n corrections that are different. So we could introduce gap assumptions in these different channels according to the different 1/n corrections, which will break the SO15 symmetry, but we're kind of limited. So the power of that is kind of limited because it's all 1/NF suppressed. I want to point out that there is a sector that is that has this large symmetry breaking factor, which is the A representation. 2 representations from the SU4 side maps to the same SO15A, which is are the adjoint spin odd sector and the AS bar spin 1 or AS bar spin odd sector. And these have a very different leading order large N predictions. The SU4 flavor conserved current lives in the 211 representation, and the 310 representation has a leading order prediction 5. So I think it's safe to say that, like, okay, so say that the leading operator in this sector is irrelevant. So that kind of brings order 1 symmetry breaking factor. But overall, since we have this huge degeneracy in the SU4, in different sectors in the SU4, the whole power of using the RRR single correlator bootstrap is kind of limited. And it's understandable if it turns out that the bounds we obtain from the RRR single correlator bootstrap is not that specific to the SU4. So it could be somewhere in the middle between SO15 and SU4, since we're doing finite numerical precision calculation. On the other hand, if we look at the monopole single correlator bootstrap, immediately we find that different representations that maps to the same SO12 representation have very different large N predictions. There are the 4 fermion operators and the A bar representation, and we have the fermion bilinear showing up in this A2211 representation. The reason why there could be such a difference is because the two representations have different parities. And we also have a monopole spectrum showing up in the T we also have monopole spectrum showing up in the T representations, and those have very different large M predictions. For example, if you look at the T220 representation that contains the leading charge 1 monopole, and we also have kind of an extra bonus from the large gap between the leading charge 1 monopole and the subleading one. So the qualitative way of understanding this this difference is because we can think of the delta 2 in this sector as a pair of fermions excited from the monopole background. So the fermions which have the scaling dimension 1, if there's no monopole background, will kind of like be corrected. So the energy of the energy per fermion kind of gets a large correction when there is a monopole background. So that makes the big difference between the delta 1 and delta 2 in the charge 1 monopole sector, which we can potentially take advantage of. So this is kind of a brief overview of like how we're going to use the large M prediction to kind of enhance the bootstrap results. And before we discuss the our results, let me introduce some previous studies. In 2016, Chester and Pufu studied the monopole single correlated bootstrap. What they found is that there are pretty strong bounds on the scaling dimension of the charge 1 monopole as a function of the charge 1/2 monopole. And very interesting fact is that the monopole large M prediction, the charge 1 monopole large M prediction nearly saturates the bootstrap bound. And there's some sensitivity to the gap assumptions that one can make on other sectors. For example, if we turn on a gap in the A bar representation, recall this is the charge topological U1 charge neutral SU4 representation 220 or SU parity even representation, parity even sector, which have a large M prediction roughly 2.4. Well, so it's at leading order, it's a 4 Fermi operator, and it gets a pretty large 1/n correction that brings it down to 2.4. So its value, it's expected to change by some amount in the subleading orders. Depending on the gap assumptions on this A bar sector, the lower bound on the scaling dimension of delta M1/2 kind of moves in a way that's very sensitive to the bootstrap bound. One can also consider introducing, consider isolating the the leading charge 1 monopole by turning on a gap above this sector. Recall that we have seen in the large M prediction that the next charge 1 monopole has a prediction of 6.1, so one can turn on some pretty large gap assumptions. And once we do that, we get the bounds becomes kind of an interesting peninsula. Oops, sorry. Which is kind of promising because it looks like the large N solution to the monopole scaling dimensions is nearly saturating the bootstrap bounds. And with some gap assumptions, one can get kind of these kinky structure of the allowed region, which could, in principle, carve out the parameter of QED3 if we keep incorporating other large N predictions. Another result comes from bootstrapping the fermion bilinear single coordinator bootstrap. And that work is done by Zhijin Li in 2018. So he found that the RRR single coordinator bootstrap has a coincident with the SO NF square minus 1 vector bootstrap. And from this vector bootstrap, he found there is a family of kinks that are positioned near the large N prediction of the scaling dimension of the fermion bilinear. So it's promising because it looks like the RRR single correlator bootstrap has a kink that's related to the QE3. And even further, he can break the SO NF square minus 1 symmetry by introducing the 1 over NF, introducing gap assumptions that break the symmetry. And those, like I mentioned in earlier slides, these effects in the RRR OPE are 1 over NF, kind of subleading in 1 over NF. So once he introduced these gap assumption from the large N expansion, he found that in the limit of NF goes to infinity, the bounds on these 4 fermion operators actually converges to the large N values, which is quite non-trivial because it shows that at least at large NF, the QED3 large N prediction nearly saturates the bootstrap bounds. So one can potentially take advantage of this. There's also work done by He, Rong, and Su in last summer studying the mixed correlator bootstrap of M1/2 and R. And they took the point of view that is slightly different. They argued that since QED3 is the Dirac spin liquid in condensed matter, which and the requirement of Dirac spin liquid to be realized on some lattice will result in additional constraints on the scaling dimension of some low-lying operators. So for example, the AA bar operator is singlet under the UV symmetry of the lattice. So in order for the fixed point to be stable, the A bar operator has to be irrelevant. And if one look at a specific lattice, for example, the Kagome lattice that they considered, the charge 1 monopole is also required to be irrelevant. So from these type of requirements, the bootstrap bounds rules out the large N prediction. And the remaining part of the allowed region prefers the Monte Carlo result that I presented a few slides ago. Since the Monte Carlo result sits in the bulk of the bootstrap bound, it is not immediately clear how to take a step further and isolate this solution using stronger bootstrap setups. So those are the previous studies. So our understanding of the situation is that there are two scenarios that are kind of both valid to our current understanding. Since the result depend on the gap assumptions, one cannot a priori tell which scenario is true, but one can keep working on these set of assumptions, and with stronger and stronger bootstrap setups, and hopefully verify or prove that certain scenarios are inconsistent in the future. So we took
Can I ask a question?
Yes.
So it was not clear to me. So it seems that a lot of the studies decided to go for this operator R.
Mm-hmm.
And it was not clear why this particular operator R and not some other operator, like why this particular combination of psi bar psi. So could you comment on why this looked promising initially, why you decide to follow the same direction?
I think it starts from this fact that there are kinks in the RRR single correlator bootstrap that are close to the Largen prediction of the fermion bilinear.
So it's this observation showed that this operator is the right thing to go.
Yeah. And I guess, if Zhijin's here, he can probably like correct me if I'm wrong, but I'm guessing like even earlier when one decides to study what operator to pick up, one needs to consider, okay, so first of all, does the OPE have kind of a reference to different non-trivial representations that shows the property of the theory? So if you start with the singlet, then it's kind of, if you start using the singlet as the external operator, it kind of hides the flavor structure of the theory, right? So that's one thing. And also you want to start with an operator that has low scaling dimension. If the external operator had very large scaling dimension, then the bootstrap bound converts slowly. This is also part of the
that uniquely fixes this operator. Is there's no
well, we have not so many two fermion operator, right? So the two fermion operators can either be singlet or adjoint.
Okay.
Yeah, can I make a comment? Yeah, so I think for Slava's question, it depends on the flavor number. So if the flavor number is very large, then the monopole sector, they will have a very large scaling dimension. So that essentially decouple from the spectrum. But then in that case, the fermion binding operators could be the newest operators in the spectrum. So for the two fermion operators, you may either it could be S3 for adjoint representation or S3 for singlet representation. So, but of course, we know that the S3 for adjoint representation carries information about the gettable symmetry. So we may expect that it can tell us more about this theory. But if we could use small flavor number, like if n of equal to 4, then from large n prediction, it suggests that the lowest monopole operator has the lowest scaling dimension. So we may expect that for the small flavor QED3, the monopole operator could be even more important to study QED3.
Yeah, these monopole scales with NF. So at large NF, I guess it's not very clear how to bootstrap monopoles. Yeah. So now, back to the bootstrap results in our work. So first, we consider the simple setup of a monopole single correlator bootstrap without any gap assumptions. So immediately, one can show that either the irrelevance of either A bar or M1 will rule out the large NF. The argument goes as the following: if we assume that the A bar has scaling dimension above 3, then that forces us to live above this horizontal red line. And that also requires us to live on to the right of this vertical red line, and that rules out the large N. and the same argument goes to the M1 bootstrap bound. Starting from that, a slightly different point of view, since as the work by He, Rong, and Su, since our goal is to verify if the large N itself presents a consistent solution to crossing, we would like, and also if we don't require QED3 to be realized in any specific lattice, then we can consider relaxing this bound a little bit to go to a bar is greater than 2.8. And besides this, we can take advantage of some of the large N predictions and recall that there's a big gap between the leading charge 1 monopole and the next to leading charge 1 monopole. The next one has the large N prediction 6.1, while the first one has a prediction 2.5. So we could choose to set a big gap above the M1, which is M1 prime is greater than 5.0. Besides this, we also assume that there's no singlet relevant scalar, which is a natural requirement if one believes in the merger annihilation scenario. So with those assumptions, we see that the bootstrap bound on the scaling dimension of delta M1 and delta M1/2 becomes kind of an interesting peninsula. And the large N solution of the large N prediction of delta M1 and delta M1/2 sits right at the tip of the peninsula. So in last fall, when David gave the same talk, there was questions regarding like how does this bound change with like the gap assumptions, and here we present the result. So if we modify this gap assumption on the A bar sector, then if we relax it, the tip structure is longer, so I think presumably we're allowing some extra solutions. And if we increase it, the tip structure still exists, but just the large N solution itself is not allowed anymore.
Sorry, is there a large N prediction for this delta AA even to leading order?
To leading order is 4, and to next leading order is 2.4. So it's kind of large, right? So we don't know where it's going to go the subleading order.
I see. Yeah. Okay. Well, I guess it'd be very interesting to compute the sub. I guess the next order. To see.
Yeah. To the next. Yeah, that would be really helpful to this study. Yeah. Okay. So this is a kind of a promising result in the sense that okay, we start from gap assumptions that are inspired by part of the large N solutions, the delta M1 prime and delta A bar. But then we can show that the bootstrap bounds kind of highlights other pieces of the large N solution, delta M1/2 and delta M1, which are not necessarily related. And even more interestingly, there is a peninsula, there's a tip structure, and the large N solution nearly saturates the bounds. And to gather some more information to this solution, we additionally calculated the lower bound on the central charge, conserved current central charge on top of the tip structure. So here I'm showing you contour plot the lower bound of the central charge, the Yuan topological conserved current central charge. And we see that the lower bound kind of rises sharply on the bottom of the tip structure. So that tells us if we believe or if we expect that the central charge does not change so much from this highlighted large N value, large N prediction, then the lower bound, the lower half of the peninsula seems unphysical. So as a consequence, the tip structure after implementing the gap, implementing this mild assumption on the central charge becomes even sharper. And remarkably, the large NF solution is the large NF prediction of the scaling dimension still sits at the top of the at the tip of the allowed region, and its value of the central charge lower bound is very close to the large N prediction. Moreover, if we want the Monte Carlo simulation to be consistent with the bootstrap bound, given other gap assumptions that we made, then we'll need a large correction to both the delta M1/2 and delta M1, which is possible. But this at least shows some tension between the Monte Carlo simulation and the large N prediction. Starting from this, we can take one step further, which is if we believe that the scaling dimension of the leading charge 1 monopole is close to its large N value, which is in the vicinity of 2.5. For example, we can make an assumption that delta M1 is lower than 2.6. Then we get a closed region with the scaling dimension of M1/2 bounded from both above and below. And perhaps also this is, also there's going to be a closed region for other operators. So we did that. And what we got was a closed region in the scaling dimension of both delta M1/2 between 1 and 1.2, and the scaling dimension of the fermion bilinear between 1.1 to 1.8-ish. So this is our best bound it's a mixture of the mixed correlator bootstrap of M1/2 and R, and the single correlator calculated at higher derivative of order. So this shows that the island here is still kind of converging, so it's going to get smaller in the with higher computing power. The current island seems to allow the large NF solution, which is kind of close to the lower bound of delta M1/2, and also have overlap with the Monte Carlo simulation result. But we're kind of convinced that the overlap region corresponds to unphysical solutions. The way to see that is by looking at the conserved current central charge bounds. And again, we see that the central charge lower bounds rises up, rapidly at the right half of the island. So if we believe that the central charge does not get too far away from the highlighted contour, then the Monte Carlo simulation corresponds to unphysical. The central charge that has the overlap with the Monte Carlo part seems kind of unphysical. So we can also show that qualitatively similar thing is happening also for the flavor current central charge and the stress tensor central charge. Basically the large N prediction of the scaling dimension is close to the value of the central charge of the central charge prediction, and the right part of the island correspond to unphysical values of the central charge. So it's kind of a non-trivial thing happening, because the input that we use as gap assumptions are some part of the large N predictions, and what we get from it is a consistency between the central charge and scaling dimension of delta m1/2 and delta r, all concentrated in the same regime. And we can also study the extrapolation of the bootstrap bound. The reason why we do this is that, okay, so we see some nice consistency, but since all of the bounds are still converging, there's the risk that, okay, so if things work too well at this current lambda that we're working, then if we increase lambda, if one of the gap assumption we made is too strong, then we could risk killing the solution, or even worse, disallowing the whole island. So we studied the bootstrap, we studied the extrapolation of the bootstrap bound of the lower bound of delta m1/2 and the upper bound of delta m1/2. And it seems that in the infinite lambda limit, the large N solution is still allowed. And it's even closer to saturating the lower bound of the delta m1/2. On the upper bound, it seems that there's still some room, and it also depends on the upper bound that we put for the delta m1 scaling dimension. And remarkably, if we choose the upper bound of delta m1 to be the large N value, which is 2.5, then the extrapolation says at infinite lambda, the upper bound of delta m1/2 is also very close to the large N result. So that means the large N solution, the large N prediction of delta m1 and delta m1/2 is consistent with the bootstrap bound and nearly saturates the bootstrap bound on both sides. And we also studied the upper bound and the extrapolation of the upper bound and lower bound of delta R, and that gives us a range at the infinite lambda limit, which potentially could imply that our current bootstrap setup is still allowing a bunch of extra solutions. The central charge bounds rises up in the infinite lambda limit. Large N is still valid and actually gets closer to the infinite lambda extrapolation bound. So all of the extrapolation is still compatible with the large N expansion if the large N expansion itself is converging. So that gives us the conclusion. So our results imply that part of the large N prediction of QED3, even at 4 flavors, provides a consistent solution to bootstrap, which in turn is close to saturating bootstrap bounds, which gives us a lot of hope that in the future we can even sharpen the bounds with stronger bootstrap setups. We have encountered a lot of difficulties bootstrapping gauge theory. One important point is the bound coincidence. And we used parity symmetry, monopole spectrum, and central charges to kind of break the bound coincidence, and we successfully obtained non-trivial constraints that we believe is specific to the 4-flavor QED3 theory. The techniques we used in this work will also shed light in generic bootstrap problems. Nevertheless, our result is still sensitive to assumptions. Some of the gap assumptions we made are not fully justified. For example, this upper bound on delta M1, we're looking forward to remove it, and delta A bar could be justified or disproved or disapproved if we have further subleading large N corrections calculated. Also, the solution may not be isolated from similar theories. And in the future, actually, right now, we are trying implementing the mixed correlators involving both the M1/2 and M1 monopoles. So the kind of the tip structure we got from the delta M1/2 versus delta M1, it's roughly kind of it's roughly close to the situation that we have for the Ising single correlator bootstrap of the sigma operator. If we put a big gap above the so if we put a big gap on the scaling dimension of delta epsilon prime, then we also see kind of a tip structure. Of course, that tip is much stronger and much less gap dependent. But if the argument goes similarly, then maybe the next step will be just mixing the operator M1/2 and M1, and hopefully this we can still get a closed region with this kind of arbitrary gap assumption delta M1 is smaller than 2.6 be lifted, so we get a closed region that is less gap dependent. We've also seen that the central charge plays an important role in QED3. So if we mix up the correlators JJJJ and TTTT, that will likely to provide some non-trivial constraints. We look forward to having more improved perturbation predictions and lattice simulation results. Those are going to sharpen our gap assumptions and clear out some potential ambiguities. Last but not least, I'd like to point out that we're currently suffering from the slow convergence of the bootstrap bound. So a lot of the ambiguities come from the fact that the bounds have not converged very well. So any numerical techniques that either allows us to calculate higher derivative order with the same amount of computing power or improves the convergence will greatly help clearing out some of the ambiguities. So that was my talk. Thank you very much.
Thanks, Yuan, for a very nice talk.
Thank you.
Are there any questions?
Yeah. So I was going to make a comment. So one of the things you were using was like the large N prediction of the Q=1 monopole operator scaling dimension, right?
Yeah.
Yeah. And so you were specifically talking about the Q=1 monopole operator, which is in the traceless symmetric representation of SO6, right? With spin 0.
Yes.
So I mean, you can use the fact that one of the results we had from the paper where we were computing Chern-Simons monopole operator scaling dimensions is that one of the results, which also applied just for this k=0 and NF=4 case, is that at leading order in the large NF expansion, there are several Q=1 monopole operators which have degenerate scaling dimensions, and so it's not just the one you talk about, which is in the traceless symmetric representation of SO6. You also have the one which is in the anti-symmetric representation of SO6 and the one in the singlet of SO6, as long as their spins are non-zero. So in particular, for the anti-symmetric representation, if it's spin 1, and for the singlet representation, if it's spin 2, then at leading order large NF, we expect it to have exactly the same scaling dimension.
So sorry, that was a bit too fast. So which two representations are you talking about?
Okay, so okay. So first of all, I'm using the language of SO6 instead of SU4.
Oh yeah.
Yeah, and so I'm saying the one you talked about was the traceless symmetric representation.
Right? So that's traceless.
Yeah. So that's the one you talk about, traceless symmetric.
Yeah,
But you can also look at the one which is spin 1 and in the anti-symmetric representation of SO6.
yeah. So that's degenerate, right?
Yeah,
That's
yes.
one, yeah.
So that's believed to be approximately degenerate.
Yes,
And then
yes.
there's also the one which is spin 2 and in the singlet representation.
Yeah.
And so because those guys, I guess, are believed to have scaling dimensions that are all kind of, I guess, roughly similar. So like, I guess whatever assumption you're putting for what you called this delta M1, you could put also for these other delta M1s.
Yeah. Actually, I have a question. So do you believe that the subleading correction to this operator also holds the same for all these 3 degenerate channels?
No. I mean, no. So like the subleading would probably be different. Because I mean, we had this prediction.
The order 1 piece, which you have calculated.
So the order 1 piece would okay, so we have this kind of like spin degeneracy breaking term, which so it depends on like the spin squared. And so that predicts that the bigger the spin, the bigger the dimension. And so that's why we believe that, I guess, like non-perturbatively, indeed, what you call delta M1 should have the smallest scaling dimension. But that term, I guess, is not that big. For the case of NF equals 4, there's something like 0.1 times spin squared. And so that's why I would think at least the spin 1 guy probably wouldn't be too much bigger than the spin 0.
Yeah, at least I think it's good to know that the higher spin guys are expected to have slightly larger scaling dimensions. So if you put a universal bound that according to delta M1, then we're safe. Yeah.
No. But I'm just saying like it's another assumption you can in principle put in, because like you were putting in this assumption that delta M1 has to be reasonably small. You could also do the same assumption for the delta M1 which has spin 1.
Oh, you're saying, okay, so other scaling dimensions also could have some like upper bound and perhaps big gaps between the first operator and the second operator. Stuff like those. Okay,
because I mean, because there's kind of a general intuition in the bootstrap that you want to put in information about all the relevant operators in order to get like nice bounds. And so I guess I'm suggesting that it's likely that this other delta M1, the one that's spin 1 and in the anti-symmetric of SO6, is probably also relevant. And so probably it would also be useful to, put in something about it.
Yeah. So we'll probably can incorporate some of these gap assumptions in the study of the mixed correlator M1 versus M1/2. And it's probably going to give us even stronger bounds, because now we're kind of like emphasizing the structures in the multiple sectors. Yeah, so those are going to be very interesting. Yeah.
So you mentioned this point in last November. So actually, after you mentioned this point, we thought about to verify this fact instead of import this fact as a double check of our result. But the difficult point is that so to extract the spectrum in these sectors you mentioned, we may either like use EFM method, but it's kind of based on our current results, the island size is very big. So the EFM do not match in different directions or different part of the island. So we cannot get a sensible result just from EFM. So another way is that we may just directly compute the upper band of the operator in these sectors. But that requires a lot of computation power, so we haven't done it yet. But I guess in future we may test this fact.
Yeah, I guess perhaps one could consider like using the navigator like setup, kind of like treating the scaling dimension of some operators in these channels as the target function, and like maximize and minimize over the island that we currently have. Yeah. And yeah, so for all of these assumptions, we can either use it as an assumption or use it as kind of like a non-trivial check that our solution corresponds to QED3. Yeah.
I was also wondering if you guys had looked at like the next lowest case of flavors, so like NF equals 6, because I mean, if you have kind of, I guess, like various qualitative evidence that maybe large NF is really matching Bootstrap, which is intriguing. If you could get that to work also for another value of NF, that would really make it much more convincing, because and it probably wouldn't be too much more difficult. I mean, I understand it's more crossing equations, but it's not that much more crossing equations.
Yes, true. For NF equals 6, it could be very interesting to study as well. But right now we're focusing on to improve our NF equal to 4 result, because apparently we're not optimizing our counter result because it takes too much time for computation.
In other words, if you learn a lot of like what we can do in bootstrapping NF is equal to 4, we can use some of these experience into like NF is equal to 6. If it works better, then it's more convincing. Yes. Yeah.
Can you comment a bit more about this prospect of using navigator? So, for example, if you just take some random points within your islands and you try to extract the spectrum and so on, do you see anything strange in this spectra that, do you see more operators than one would expect to see or something like that? Did you do this checks?
So we did check the EFM. We didn't do a very comprehensive study of the EFM, but basically on this island, let me think. I think we've checked that the scaling dimension of, let me see.
Actually, we checked the we actually in our paper we have like the peninsula structure and design. If we try to bind the like a minimum of the CG central charge, then there's a local winding and on the peninsula structure, and then we extract the EFM and on this local winding, and then indeed we can find some pattern in some non-singular sector.
You want to say that? Yeah.
But the problem is that in singular sector we expect that there will be low line operator which have large in prediction about the 4 plus or minus 1 in correction, but it's very hard for us to reproduce such two nearby operator in the singular sector.
Yeah, the singlet sector looks like it's not converging to the, well, so basically, first of all, not the whole island will correspond to the same EFM. So the EFM of these region and also these region are gonna have like very different result. And also depends on what parameter we choose to maximize / minimize. And specific to the central charge minimization, we found that if near the large N solution of large N prediction of the scaling dimension, if we look at the EFM of central charge minimization of I think either the topological Yuan or the flavor group, we found that some of the spectrum, I think the sort of the T0 sector and the like A bar and SS bar are all kind of staying at physical values. We didn't really understand what is happening for the singular scalar sector. Like we have a gap assumption saying that it's greater than 3, but what we found is that it's basically some value like some value around 4. But it could depend a lot on what you do for the like maximizing like what parameters you maximize / minimize and like where you choose to do it. Yeah.
But if everything looks fine, then why do you think that navigator could help?
We haven't really studied the monopole spectrum using this method. So perhaps, yeah, so we basically have focused on the fermion sectors, which are already kind of ambiguous because the large N correction is kind of large. But if we could verify some of the, if we can verify some of the predictions in the T representation, V representation, those charged, those sectors that are charged under the topological U1, like if we can find some of these, like if we can find structures that are qualitatively similar to the pattern shown up that we show in this table, then that gives us more hope in like arguing that a certain solution is corresponds to QE3, not some arbitrary unphysical solution. Yeah, but right now, I think we need better bootstrap constraints. Yeah, if we can shrink the island to more constrained region to be near the large n, then we can like make such argument. But with such a large island, if we study globally the EFM, then we don't expect to see the structure of the solution. Yeah.
Okay. Any further questions? Well, if not, then let's thank Yuan again. Thanks, Yuan.
Yeah. Thank you very much.